So what is a microcontroller? A microcontroller is a programmable integrated circuit on a chip that can do a specific task. They are like a basic processor that can only run one program at a time. Since microcontrollers are so small, they are perfect for putting in many devices that need some type of processing ability. Some devices you will find microcontrollers in are TVs, microwaves, cameras, and DVD players. Some people have even made remote control gadgets such as quadricopters with microcontrollers. So you might be wondering how a microcontroller is different from the CPU we have been studying in class. Well, actually, the microcontroller has a CPU in it. You can think of a microcontroller much like your personal computer, but it's much smaller and all squeezed onto this tiny little chip. Inside this chip is the processing unit to do the logical and mathematical operations. It also has memory so that it can store the program it is running, and it has a clock that is derived from an oscillator. The microcontroller also has some type of input and output. So if you want to do some type of I/O with the microcontroller, you just must hook up the I/O pin to some type of digital logic. So here we have a better view of what is inside the microcontroller. On the top there we have the processor core, or the CPU. In the middle we have the clock that keeps its timing, the RAM, and the data storage for whatever program might be running on the microcontroller. Then we have the peripheral bus, and that is for the I/O that you could connect to it, and you can hook up a number of different things to that. Why should you use a microcontroller over a CPU? Well, this really depends on the application you are working on. We don't use microcontrollers in your personal computer because they don't have the processing power you need to run a full OS and multiple other programs. Like I said before, the microcontroller is for one single task, whereas your personal computer is running multiple tasks at the same time. This is what's nice about microcontrollers, is that they use very little power to run and don't dispense a lot of heat, though they are much slower than the CPU in your computer. They are also much cheaper than your computer's CPU. Microcontrollers vary in price, but some are only a couple dollars, and generally not much more than 30, whereas the CPU in your computer was probably over a few hundred. This is why microcontrollers are so great for little projects like an alarm clock, or like setting the cook time on a microwave, or even home automation. But this would take multiple microcontrollers.
The visible part of the microcontroller is called the package. The package consists of the molded plastic, or in some cases ceramic, housing that protects the inner components of the microcontroller. The package also consists of the metal tines that provide a way for the microcontroller to connect to a printed circuit board. The printed circuit board is how the microcontroller can interact with other peripherals such as the servos and LED lights that you'll see later in this video. Now, in order to fully understand the differences in packages, I'll have to explain a little bit more about printed circuit boards, or PCBs, and how they're attached to the microcontroller. The PCB consists of a piece of non-conductive material, such as some kind of plastic or fiberglass, an etched piece or several pieces of extremely thin copper, and a non-conductive laminate that keeps the etched copper in place on the chip. These can also have multiple layers of conductive material padded by non-conductive material connected by what are called vias that allow for a greater amount of connections in the PCB. There are two ways to attach electrical components such as a microcontroller to the PCB. That is the through-hole and surface mount methods. The through-hole method of connecting components involves drilling holes through the PCB and using both sides of the board to make connections. So you have a layer of conductive material on the top and bottom of the non-conductive material with a hole drilled in it that connects both sides. This was used more frequently during the 70s and 80s than now, but it took up too much space since one had to account for holes on both sides of the card to work. Also, this interfered with multi-layer PCBs, since there were multiple layers that all had holes in them. There's also the surface-mounted method of attaching components. In this method, the components are attached directly to the surface of the PCB using solder and epoxies. This facilitates the use of multi-layer PCBs as there aren't holes drilled through the entire card. However, Through-hole PCBs are still used today as they are more resilient to jarring or damage than the surface-mounted cards. So if a piece of electronic equipment has to be handled roughly, it is likely that it has a through-hole PCB on the inside. Now we have to get back to the packages. There are 4 types of packages I will be discussing in this video. They're the dual inline packages, or DIPs, small outline integrated circuits, quad flat packages, and the ball grid array package. Dual inline packages were the first type of microcontrollers implemented. As you can see in the picture, they're used in through-hole type PCBs. You'll recall using these types of chips in the breadboard labs from earlier in the semester. Small outline ICs are similar to dual inline packages, but as you can tell by the seagull wing style pins, they're used on surface-mounted PCBs. Quad flat packages came about later and allowed for double the connections of a similar dual inline or small outline package. This increase in connections allowed for more powerful chips that could use more energy and also do more complex operations. Finally, we have ball grid array packages. These allow for the most amount of connections by including a miniature PCB around the outside of the microcontroller that is covered in small balls of solder that serve as the connectors. These must be used with a surface mount PCB. This is, in theory, the best chip that mentioned so far. However, these chips are impossible to install by hand and are difficult to troubleshoot if there is a connection problem. Also, the equipment that is required to make these chips is extremely expensive.
Now comes the fun part, programming a microcontroller. First off, what do you need to do this? Well, of course, you need the microcontroller itself, and best pick the one that is best suited for whatever project you're working on. Next, you need a programmer. This is a physical device that you hook up to the microcontroller to turn your code into a machine language that the microcontroller will be able to read. And this is not something that turns caffeine into code. Those are 2 completely different types of programmers. Next, you'll need an IDE. Some companies that make the microcontroller and programmer have their own, but other companies just have a tool that you can plug into Visual Studio. Next thing you need is a little bit of know-how how to hook up the programmer to the microcontroller. This is just a little bit of circuit work. So here we have a basic program that can be ran and synced to the Arduino. Right here we are setting LED to pin 13. We are setting pin node to pin 13 and saying it has an output. Right here we have infinite loop. This loop is just going to get run on the Arduino until it's turned off. So right now we're writing to this output pin, pin 13. That is the LED. This is a 1, or it can also be high voltage. Right here we are delaying for a second. So we are turning the LED on and then waiting for a second. Right here we have the same LED and setting it to 0, but this can also be low. So all this program does is blinks the light on and off. And here we have that very basic program loaded onto the Arduino itself. As you can see, the positive end of the LED is in port 13 and the negative end is hooked up to the ground. Here is the microcontroller that is storing the program and currently running this simple little blinking application. Here is another Arduino example showing you how easy it is to set up a servo. So first we include the servo.h file. We make a new servo object. I'm keeping the light in here because we all like flashing lights. Next I gotta attach my servo to pin 9. So this is just the output pin, pin 9. And then I am writing microseconds 1500. This makes it go right. I'm delaying it for a second. I'm writing microseconds again 1000. This makes it go left. And then I'm writing microseconds again 2000. This makes it go back right. And now I'll check to make sure everything compiles correctly, and we are good to go, and I'll show you that how it works. So here is that servo example. As you can see, I have the servo hooked up into pin 9. Here is the voltage. It's hooked up to 5 volts, and that's coming right from the power supply. And it's also hooked up to the ground. So it's really easy setup to hook up a servo to the Arduino. And there's the servo. So once I plug it in, since I already flashed the program on the microcontroller, it'll just start up and I won't have to compile it again. So it's loading, and it's loaded. And that is really how easy it is to set up an Arduino with a servo. And that servo will just keep going back and forth until the program stops, which won't be anytime soon since it's in an infinite loop. And that is our overview of microcontrollers. They are really good for very small projects that only require one task. Like you saw the Arduino running, it was just running one program at a time. Every time we wanted to run a new program on it, we had to reflash the microcontroller. We also talked about the different packages and their different designs. We gave you an overview of the code and the types of IDEs you could use. And we showed you a couple examples on the Arduino.